Hello everyone, today we're going to talk about low rank models. You might notice that the sound in this video is much better than in my past videos, which had this weird echo that I had tried to desperately attenuate by crazy stuff like putting a mattress here and putting a lot of random things in my living room, following some advice I read on the internet. So it turns out that the reason was that the mic in my webcam was on and that was producing the weird echo. So I just wanted to apologize about that. Those of you that know me, unfortunately, won't be too surprised by this. But anyways, let's talk about low-rank models. Today, our goal is to describe low-rank models, explain how to fit them to data, and show an example to some real-world weather data. The prerequisites are principal component analysis. As we will see, the techniques that we use to fit low-rank models are essentially equivalent to PCA. All right, so what we want to do is we want to analyze matrix valued data. What do I mean by that? I mean that every data point is associated to two different entities. Okay, it's not that it has two associated features like height or weight. No, it's associated to two different things. So it's easier to see what I mean with examples. For example, in a recommender system, you might want to predict, for example, whether some users are going to like some movies or whether some users will be interested in some product. In this case, your data points are ratings given to movies by users. So we have, just to be clear, each data point is indexed by two indices, one that refers to the movie and another one that refers to the users. All right? Another example, in computational genomics, you might be analyzing some single cell sequencing data, and you might have expression levels of different genes in different cells, because maybe some cells have cancer and you want to see if their expression levels of certain genes are higher in those cells or something like that. Again, your data points have two indices. Okay, the index I in this case is associated to a gene, and the index J is associated to a cell. And the final example is the weather data that we're actually going to look at later on. So you might have temperature measurements, and each data point is associated to a location and the time at which the measurement was taken. All right, so a very useful way to analyze this kind of data is to assume that the data actually depends on a small number of factors that are associated to each of the two indices. We write these models in the following way. So here we're assuming that there are R factors, okay? R factors. And these R factors are combined additively to approximate each data point. So this approximates the data point Dij. How does it approximate it? It approximates it with a linear combination of terms where each term has two parts that get multiplied together. This part is associated to the first index. So let's think about movie ratings. This part would be associated to movies, and this part would be associated to the user. So we have R terms. This means that for each movie, there's going to be R coefficients like this that we're going to need to learn. Okay, and it's going to tell us how each movie is associated to each factor. So there might be a factor, for example, that captures whether the movie is a romantic movie or not. Okay, and if it's a romantic movie, then this might be higher. And if it's not, it might be lower, for example. Or another factor could be if it's an old movie, or if it's a very popular movie. These are going to be data-driven factors, so we can't really predict what kind of factors are going to be associated to the movies. And then conversely, we have the coefficient BLJ, which is associated to the user. And that tells us how that user is associated to the same factor. So if one factor, for example, captures romantic movies, and we're going to see some examples a little bit later on, this other coefficient tells us for each user, does user J like romantic movies or do they hate romantic movies? okay? So that's how we build every data point. So for every data point, we say, okay, we have R factors. For each factor, what is the coefficient associated to this particular movie for that factor, and also to the user, right? So there's two coefficients for the movie, coefficients for the user associated to each factor. We multiply them together, and then we add these R terms together. That is a low rank model. And the intuition is that we think that in this case, the movie ratings or the data are driven by a small number of factors that can be learned directly from the data. If you think about it, essentially what we're saying here is that our data, I'm gonna draw a picture now. So I'm gonna change the color. I think I'm gonna use purple. So we have this big matrix of data that is n1 by n1. What we're saying is that we can express it approximately as the product of these factors. I'm just looking for the blue color. Here we are. Okay, no, actually I want to make this a bit prettier. As you can see, I can't really draw straight lines on my own. Okay, so what we're saying is that we are going to express this big matrix that is n1 by n2 as this product of two matrices, which are n1 times r and n2 and r by n2. Okay, if you look at a point here, it's going to be equal to the corresponding row here, okay, times the corresponding column here. Okay, this is exactly what this sum is doing. It's a linear combination of these R terms. Okay, like this guy gets multiplied by this guy, it gets added to this guy multiplied by this guy, and so on and so forth. So what are we really doing? We're taking our matrix of data and expressing it as a low rank matrix. So you don't remember what the rank of a matrix is, you might want to brush up a little bit on that, but essentially a rank of a matrix tells you how many linearly independent columns there are in the matrix. And here we see that there are R independent columns because we can express any column here, if this is true, if the equality is true, as a linear combination of these columns. The same for the rows. So matrices are weird that way, where if you can, the rank in terms of the columns is exactly the same as the rank in terms of the rows. And you can see it very clearly here, right? Because the rows of this matrix, if the equality holds, can be expressed as linear combinations of the rows in the red matrix. Okay, so this is what a low rank model is. We want to approximate our data as this low rank matrix. And the motivation is that we think that there's going to be a small number of factors that are actually driving the data. I don't know if that is a thing, driving the data, but you know what I mean. And we can learn them in a data-driven way. I feel that I'm saying data a lot, but I guess that's okay. Okay, so the rank of L here of our approximation is R, as you saw from my picture. This might remind some of you about PCA, okay? And I think it's actually kind of clear in this picture. So let's see if I manage to remove some of the arrows that I drew. So if you think about it, what are we actually doing here? We're taking each column, here, okay? And what are we doing? We're expressing it. So what is that column going to be equal to? It's the column of this matrix, okay, times this whole matrix, okay? So what are we doing? We're doing dimensionality reduction, because now we could express, and go check out the video on dimensionality reduction using PCA, and this will become clearer, but PCA allows you to do this. Okay, it finds like a linear dimensionality reduction so that you can express a big vector with a smaller vector of coefficients in a certain basis that is chosen so that this is optimal in a certain sense. Okay, so that's what PCA actually does. So how about we just fit the low rank model using PCA? And in fact, we can. Essentially, what we would do is we would build the covariance matrix of the columns that looks like that. Here I'm using Python notation, where this is each column. Amazing. Wait, let me try that again. Each column of the outer product, we take the average of this. Equivalently, that gives us the sample covariance matrix. So we're interpreting each column as a data point with n1 features, right? Because we have n1 rows. Because remember that the big matrix has n2 columns, n1 rows. So we can interpret the matrix as not in matrix form, but just saying, okay, I have n2 rows, n2 columns that have n1 features. I'm going to apply dimensionality reduction using PCA. How do you do it? You compute the sample covariance matrix, which actually equals just DD transpose. You can work that out. And then you're going to get your eigenvectors, and you're going to do exactly what I just said. You're going to use them to compress each of the columns in the big matrix. So here, I like to actually draw these things even for myself sometimes. So here what we have is each of these eigenvectors of the sample covariance matrix applied to applied to each of the columns in our data matrix. And this gives you a coefficient, a single coefficient that we call a principal component in principal component analysis. And that allows you to build your low rank model by saying that the entry ij of this low rank entry is going to be a linear combination of the R first principal components multiplied by the corresponding eigenvector of the sample covariance matrix. And again, this is exactly the picture that I drew here. Okay, and actually I like this picture so much that I'm going to copy it because we might refer to it later on. So I'm going to copy it. Okay. But now you might be wondering, okay, you've done this for the columns. From the point of view of compressing the columns and preserving the variance in the columns, this is actually optimal. We proved that when we were talking about dimensionality reduction using PCA. But why did you use the columns? Why didn't you use the rows? Okay, I mean, it seems kind of arbitrary if you think about movie ratings and users, or like the computational genomics example, or the weather prediction example. Why do you interpret each column as a data point with n2 features and not each row as a data point with n1 features? Why don't you do that? And that's a very good point. Okay, so yeah, bravo for that point. We can in fact do that, right? We can interpret the rows as sets of vectors. What are we going to do? We're going to reduce dimensionality of the rows in this case by applying PCA using the sample covariance matrix of the rows. So now here, I'm going to again, in this case, this sample covariance matrix is going to be like, I'm going to put a row here, and let's assume that is actually rectangular, and another row there. I'm going to compute this outer product. I'm going to sum over all the rows. That's going to give me the sample covariance matrix. This is exactly equivalent to doing 1 over n d transpose d. Remember that for the columns we were doing sorry about that. For the columns we're doing d transpose. That's the difference. Okay, so we would do this and we would get the R first, the R eigenvectors associated to the R largest eigenvalues, and we would compute the principal components. And and then how do you compute the principal components? You have to do the inner product with those eigenvectors. So the eigenvectors, this is a row, just in case you're confused, again by Python notation. Well, one would think that would be a little bit better at this. Okay, by Python notation, we have a row di here, and we multiply it by the corresponding eigenvector of the sample covariance matrix of the rows to get that coefficient, and that gives us the principal component. Okay, and then we build the low rank model by multiplying the R first eigenvector that we computed with these coefficients. And then here's where I'm going to try to paste my drawing. So let's put it, for example, here. Okay, success. I'm going to erase some of this stuff. Not that. Let's see if I can, erase in a bit more. Okay, maybe I won't erase. Now, so we were doing the columns. Now what we are doing, just to be very, very clear, I'm going to use a different color. We're doing the rows. So now we're saying it's the rows that are the examples with N2 features that we are interested in. So like doing the eigenvectors of the sample covariance matrix of the rows gives us this basis of R vectors that we're going to project on, and then we compute these coefficients and we just can put them in that matrix. Okay, so this gives us two alternative ways of computing a low rank decomposition, or a low rank model that seem quite reasonable. One of them is optimal in terms of preserving the variance of the columns. The other one is optimal in terms of preserving the variance of the rows. So which one is better? It turns out they're completely equivalent. And to see why, we have to introduce a very important tool in linear algebra and in data analysis, which is the singular value decomposition. So it turns out that any matrix, real valued matrix, is going to have an SVD that consists of, SVD is singular value decomposition, that consists of three matrices. So we can decompose the matrix D into the product of a matrix U that has orthonormal columns, a diagonal matrix S that is diagonal, and a matrix V that has V transpose that has orthonormal rows. Okay, so here is the picture. Orthonormal columns, diagonal matrix, orthonormal rows. The reason that the SVD exists is because of the spectral theorem. I will do a separate video where I will prove that it actually exists, because otherwise this video would be too long and I don't want to torture you. So important, the singular values are positive real numbers. The left singular values are orthonormal, so they're orthogonal. They're orthogonal and also unit L2 norm. And the right singular vectors, which are the rows of V transpose, are orthonormal also. They're also orthogonal and they have unit L2 norm. Okay, so maybe I'll draw a picture. We had our matrix. And what we just found out is that we can actually express this matrix as a product of three matrices that, that look like this. This is the U matrix, then a diagonal matrix that I'm going to do maybe in, okay, here the number of columns should be the same, so let me try again. And the V transpose. Okay, we're gonna pretend that all of these guys have the same number of rows, and let me write down. This is D. This is U. This is actually completely equivalent. It's equal S V transpose. Okay, this is what the SVD says. and what happens if the matrix is rank R. Okay, we see it here. If it's rank R, then the corresponding singular values are going to be 0. So what's going to happen, because the singular values are going to be 0, like only this part matters. So we can completely ignore this part and this part, and we're going to end up with a low rank matrix decomposition, which is exactly what we want when we're fitting a low rank model. Okay, I actually like this picture quite a bit, so I'm going to copy it and maybe we'll use it a little bit later. Okay, all right. So the singular value decomposition, the SVD, gives us this decomposition of the matrix D. We can write it out in the following way, which is very useful. I'm going to paste this thing here. What we're saying here, and you should actually check this on your own if you don't believe me, is that we can actually expand this product in the following very useful way, which is we sum from I equals 1 to n1, and we're going to get Si. Wow, that should have been a, that definitely doesn't look like a little square. Okay, little square, and then times column of U times a row of V. This row should be much bigger, much longer. Okay, so this is exactly what we're saying. Just to be clear, this is S, okay, I used L, so let's SL, UL, VL. And notice that this matrix here is a rank 1 matrix. Okay, so we can decompose the matrix D into a sum of rank 1 matrices. And it's super important that you understand this. So if this doesn't make a lot of sense to you, just work it out on your own. Okay. So in order to motivate how we're going to use the SVD to perform low rank approximations, to fit a low rank model, we need to define an inner product for matrices, and we'll see in a moment why this is super useful. Okay, so the way we're going to define an inner product for matrices is, imagine you took all the entries in a matrix and you made them into a really, really, really long vector, and then you said, okay, I'm going to use the normal inner product, the Euclidean inner product between vectors, where we just multiply their entries and sum everything up. That's the norm that we're going to use. It has a fancy math name, which is Frobenius inner product, but that's all it is. Okay, so it's exactly equivalent to multiplying the entries of one matrix times the entries of the other and summing everything up. These are n1 by n2 matrices, not n by 1, n1 by n2 matrices, so that's why you see n1 here and n2 here. It's very convenient to write this in terms of the trace of A transpose B. So this is a matrix, right? You take A transpose, so if A is like that and B is like that, we can take A transpose B, okay? Again, pretend that then dimensions are more or less okay. So this gives us a very big matrix. This gives us a very big matrix that is like this. So you can check, and you just need to check this, which might be surprising the first time you see it, that if you look at the diagonal of this guy, you sum across this diagonal, you get exactly this sum. Okay, like you're going to get the product of each entry of the matrix times the corresponding entry, and then you're going to add them up. It actually makes sense if you realize how the matrix product works. Okay, this is going to be exactly equal to that. Interestingly, you can also take, so this is actually equal also to trace of B A transpose. So you can kind of cyclically shift. You will see that the matrix product still works, and you get exactly the same result. Notice that, of course, these two matrices, A transpose B and B A transpose, are completely different dimensions. But if you add the diagonal, that's going to be exactly the same, and it's going to be equal to this inner product. And that's going to be a little bit important in a moment. So that's why I'm pointing this out now. Okay, so associated to this norm, to this inner product, we have a norm, which is obtained by taking the inner product of a vector with itself and taking the square root. So just standard stuff. This is how you get the L2 norm from the Euclidean inner product. Okay, and it turns out that this is just the sum of the squares, the squared entries in the matrix, and then you take a square root. That's what it is. And because of this, we can express this in terms of the trace. We can take square root of the trace of A transpose A. Very good. So now let's go back to our single value decomposition. We can think of this singular value decomposition that I drew as a sum of weighted rank 1 matrices that are of this form. So now we're going to interpret these rank 1 matrices as vectors that have this inner product associated to them. And again, this hopefully will make sense in a moment, because we have a linear combination of those vectors that are rank 1 matrix. I'm saying vectors because usually you think of a vector as a list of numbers, but there's this other meaning of vector from the mathematical point of view, which is something that lives in a vector space. So that if you add two vectors, then you also get a vector. So in that sense, matrices can also be interpreted as vectors. Okay, I don't want to get very mathematical here, but that's why I'm saying, okay, we're interpreting these matrices as vectors. That's what I mean. If I sum these two matrices weighted by some numbers, I'm also going to get a matrix. Okay, so if that is a little bit confusing, you might want to review vector spaces. Anyways, we have this sum of rank 1 matrices, and now we're going to take a look at what norm these rank 1 matrices have. The norm can be written in this way, okay, trace of this times this, and now we're going to do this trick that is used all over the place when you are manipulating matrices in this way, where we're going to move this guy here, because we can, right? Because the trace of A transpose B is equal to the trace of B A transpose. Okay, we can do this cyclical shift. And when we do that, we realize that we have the inner product of this vector with itself and this vector with itself. And remember that the left singular vectors and the right singular vectors form an orthonormal basis. In particular, they have unit norm. So this thing is just equal to 1. So this rank 1 matrix we can think of in some sense as a vector with norm 1. Okay? Now let's see how these matrices are related. So I'm going to take one of them and then a different one, and I'm going to take a look at their inner product. Okay, that's the trace of one of them transpose times the other. Okay, remember. And now we're going to do the same trick again, where we're going to move this around, and when we move that around, oh, I don't know what I did there. Just a moment. Yeah, I see what I did there. For some reason, I went back to the beginning. This will just take a moment. Here we are. So again, I'm back. We're computing the inner product between these rank 1 terms in that sum. We do this trick where this guy is going to go there. Okay, and that preserves the trace. Again, trace is just sum of the diagonal. And when that happens, we get this inner product of between orthonormal vectors, so it has to be 0. Actually, both inner products are 0. So this is kind of interesting. We have a sum of rank 1 matrices that we're interpreting as vectors in this vector space of matrices that are orthonormal. So, if I look, since they are orthonormal, this is going to have like two interesting consequences. The first one is that we can express the Frobenius norm of the whole matrix in terms of just this coefficient. Why? Because these guys are orthogonal in the inner product associated to this norm. So by Pythagoras' theorem, this is equal to the sum of the norms of each of the terms, okay, because they're orthogonal, again, just by Pythagoras' theorem, or you can just expand it and you will see, because the cross products are going to be equal to 0 because they're all orthogonal. And now we can just take this out by homogeneity of norms. So we get the squared singular values, and we remember that the norm of each of these rank 1 matrices is just equal to 1. So it turns out that the norm, if you want the energy, if we want to get a bit metaphorical, the energy of the whole matrix is equal to the sum of the squared singular values, and it's kind of spread out in each of the terms, right? Because each term is associated to one singular value, and these things are orthogonal. So if we want to compute a low rank approximation, what should we do? We should keep the R terms that have the largest singular values. Usually when in the singular value decomposition, the R, they're ordered. So S1 is the largest singular value, S2 is the second largest, and so on. So we basically take the first R singular values, and that gives us a low rank matrix decomposition. Okay, so now we can think of what is the error that we're making when we do this low rank matrix decomposition. Well, remember that this guy is equal to exactly this, but from 1 to n1, and we're subtracting the R first terms, okay, which are these guys. So then we're left with the last terms, which go from R plus 1 to n1, making exactly the same reasoning as before. We have that this is just equal to the sum of the remaining singular values. That's the remaining energy. That's the error that we're making. And it turns out that this is optimal. This is not obvious. It follows from the fact that PCA gives you optimal dimensionality reduction. That's a bit of a spoiler, but I'll prove this in a separate video because it gets a little bit hairy, a little bit complicated. Okay, so we've seen how to do low rank decompositions using PCA of the columns, using PCA of the rows, and using this singular value decomposition thing. So what's up? Like this is a little bit confusing, right? We have these three ways of doing low rank decompositions. What's up with this? I just told you that the SVD one is optimal. So then why did I tell you about the PCA decompositions? Okay, so let's go back to them. Let's remember that for the PCA of the columns, what we did is we interpreted the columns as a set of vectors and we reduced the dimensionality, okay? How did we do that? We computed the covariance matrix, which is equal to this. Covariance matrix of the sample covariance matrix of the columns. Now let's plug in the SVD, the singular value decomposition of D, in this expression, okay? Here it is. Remember that the rows of this guy are orthogonal. They form an orthonormal set. That means that V transpose V is going to be equal to the identity matrix, okay? So now what I have is U times a diagonal matrix times itself, so you're just squaring the diagonal, times U transpose. If I put the 1 over n2 here, this is actually an eigen decomposition, right? As you can see, because I have orthonormal vectors on the one side, a diagonal matrix of eigenvalues, and orthonormal vectors on the other side. So this is the eigen decomposition that we know exists because of the spectral theorem. So when we do PCA, what are we going to find? And if we pick, especially if we do PCA and we pick the first R eigenvalues, the first R eigenvalues in the sense that we're going to pick the eigenvectors associated to the largest eigenvalues, well, we're going to end up picking the left singular vectors, okay, because these are the left singular vectors of the matrix D associated to the R largest singular values, because we see that the eigenvalues are equal to the squared singular values. Okay, so that's what we obtain. So maybe you see where this is going. Now we're going to look at what the principal components, the corresponding principal components look like. Remember that the principal components are obtained by multiplying the eigenvectors of the sample covariance matrix by the columns, right? So now let's express this guy in terms of the SVD. In terms of the SVD, we have this sum. Here actually I made a mistake because this should be n1, right? Because I'm not assuming that D is low rank. So sorry about that. It doesn't really matter. Why? Because when we express it in this way and we take this inner product, just to be clear, Okay, like because it, and this I actually recommend that you do it when you're looking at expressions like this and suddenly you get a bit confused, like what is this? What is this? Like what are all these different terms? Well, just even make a little drawing. So here we have UL that looks like that, and it's multiplying a certain sum. Okay. You might be hearing my mobile phone that I forgot to turn off, so sorry about that. Hopefully they'll give up soon. A sum of something that is a number, that is SK. Okay, that's a number. Something that is a vector, that is UK, and something that is another number, which is the jth entry of VK. So we have an inner product at the end of the day. Here you realize that it's an inner product between UL and these different vectors UK. Okay, that's what we have. And all of those inner products are 0 except the one corresponding to UL. So this is just going to be equal to the singular value times that entry in the right singular vector. So when we put it all together and we take a look at the low rank model given by doing principal components on the columns, if I plug in what we just found here, we realize that it's exactly equivalent to performing the SVD decomposition. The only thing is that we're merging the singular value and the right singular vector. Okay, and that gives us, but it gives us exactly the same low rank approximation. Okay, so they're completely equivalent. And now, because I'm a bit OCD, I'm going to make sure that this is N1. All right. So what's going to happen with the PCA of the rows? You might be imagining it. So when we are doing PCA of the rows, we look at the sample covariance matrix of the rows that can be written as D transpose D. Let's plug in the SVD. Boom, what happens? Again, U has orthonormal columns. So when we do U transpose U, this is just going to be the identity. So it's going to disappear. And we end up with an eigendecomposition where we have on the left the right singular vectors and on the right singular vectors transpose. So we have an eigendecomposition. When we pick the R eigenvectors corresponding to the R largest eigenvalues, what are we going to end up with? With the first R right singular vectors, because the first R right singular, the first R singular values are the largest singular values because we order them. So now when we compute the principal components, what's going to happen? Now we're doing the rows. Okay, these are rows. So again, now we have like this linear combination of, maybe I'll just do it again, just to make things super clear. So we have a sum of what? We have a sum of this number, this entry, wow, this circle for some reason, this entry of that column vector, and this this right singular vector. Okay, and this gets multiplied with what? It gets multiplied with this eigenvector of the sample covariance matrix, which is nothing else than the elf right singular vector. So what happens is going to be, and again, pretend that they're equally thick, right? Like this row and that column. So all the inner products are going to be 0 except when Vk is equal to Vl, and then it's going to be equal to 1. So you obtain that term. When you combine it with the other one, you realize that when we were doing this low rank approximation using the PCA of the rows, what were we doing? Well, it's exactly the same as doing the SVD and then merging the singular value and the left singular vector. So this is exactly equivalent. So it turns out that doing PCA on the columns to obtain the low rank approximation is exactly equivalent to doing PCA on the rows to compute the low rank approximation, and also equivalent to just taking the SVD and truncating it. Okay, that's they're all equivalent. Let's take a look at some examples. First, we're going to start with a very simple example where we have movie ratings. In another video, I'm going to show you what happens when some of the movie ratings are missing, because that's really what we care about in practice. But first, we need to understand what happens when they're not missing. So these I just made up. These are 4 people that have watched 6 movies. So these are the 4 people. These are the 6 movies. And they're giving ratings to the movies. So for example, Mary really liked The Dark Knight and hated Pretty Woman. Okay. I don't know, Molly didn't like Spider-Man 3, but liked Love Actually a lot. Right? I don't particularly like any of these movies. So it's not that, you know, I would have maybe like 2s and 3s. Anyways, I'm rambling a bit because I haven't slept very much. My 3-year-old daughter like woke me up at 4 a.m. So, you know, maybe some of what I've said during the video is nonsense. I hope not. So how are we going to analyze this data? Okay, let me get back to this. First, we're going to center the data. We're going to see in a moment why it's useful to center. So we're going to subtract the mean. We're going to add all of these guys up, see what the mean rating is. It's going to be like around 3. And we're going to subtract it. And then we're going to compute the SVD. Okay, so when we compute the SVD after subtracting the mean, the reason why basically we're subtracting the mean is if we don't, that's going to usually be the first component in a low rank decomposition. It's not going to be very interesting, so we just subtract it. When we compute the SVD, what we notice is that the first singular value is much larger than the rest. And remember that in a way, the singular values tell you how much each of these rank 1 components in the SVD, how much energy they capture from the whole matrix. So in this case, it seems that the whole matrix is almost rank 1 after we center. So this suggests building a rank 1 model for this data. How do we do it? In this time, like usually we have to sum R terms. Here we just have 1. Okay, and then we're going to add back the mean because we need to see whether we're approximating the ratings well. So let's see how good this rank 1 approximation is. It's actually pretty decent. Here in brackets, I'm showing you the original rating, and then you have the rank 1 approximation. Notice that because of the rank 1 approximation, we're constraining the rows once you subtract the mean to be linear combinations. Sorry, not linear combinations, but like exactly the same, except they're multiplied by a certain number. And same for the columns. Okay, that's what we're constraining when we're saying that this thing is rank 1. So there's kind of perfect correlation once you remove the mean. And in this simple example that I made up, that's, you know, approximately the case. And yeah, so the approximation is pretty good. Now we're going to use this simple example to delve a little bit deeper into how you can interpret the singular vectors, because that ties back to what I was talking about at the beginning about these factors and how each movie is tied to a factor and so on. In this case, we just have one factor. In order to analyze it, what we're going to do is we're going to look at the first, at the first left singular vector. Okay, that's going to connect movies to the factor. So when we look at it, we see that some movies are negative, okay, and then some movies are positive. And we see that in this case, it just so happens that the superhero movies are clustered, are all positive, and the romantic comedies, if you want, are negative. No, the other way around, are positive. The romantic comedies are positive, and the superhero movies are negative. The sign is actually completely irrelevant. The important thing is that they have opposite signs. This means that a bunch of people kind of liked romantic movies and didn't like superhero movies, and the opposite. And because of that, we have this factor that explains a lot of the data. When we look at the right singular vector, that ties the users to the same factor. So this will tell us whether each user likes romantic movies or superhero movies. So it turns out that Bob and Molly, we need to work this out. Okay, so the positive entries were the romantic comedies. So Bob and Molly like romantic comedies because when we build the low rank estimate for Bob, what are we going to do? We're going to take this 0.48 and we're going to multiply it by each of these guys and then by the singular value. And the superhero movies are going to be multiplied by something negative. So when we add back the mean, it's going to be low ratings. The romantic comedies are going to be multiplied by something positive. So when we add back the mean, it's going to be very positive ratings. And the opposite is going to happen for Mary and Larry, who apparently like superhero movies. Okay, so hopefully that allowed you to visualize a little bit how the low rank decomposition ties back to these factors that I was talking about in the beginning. I want to emphasize though that this type of interpretations are very, very useful, but when you have a large number of, like when you have R equal to more than just a few, okay, here R is equal to 1, in our next example R is going to be equal to 3, and that's going to make things very interpretable. If R is equal to 100, it's going to be much more difficult to take a look at the singular vectors and make any sense of them, although they might still allow you to cluster the movies and the users in some meaningful way. And part of the problem is that the singular vectors are constrained to be orthogonal, which is great in terms of doing mathematical analysis, but there's no reason to constrain these factors necessarily to be orthogonal. Okay, and that's why we have methods such as non-negative matrix factorization that try to enforce structure in the factors when you're learning the low rank model. Okay, so let's take a look at our real data example where we have a data set of hourly temperatures at 134 weather stations in the United States. These temperatures were taken over a whole year. What are we going to do to analyze this with a low rank model? We're going to remove the mean and we're going to compute the SVD. When we do that, we see that, and like I want to emphasize that this is a logarithmic axis. The vast majority of the energy in the data is captured by the first singular value, and then quite a bit of energy is also captured by the second one. So it seems here that a rank 2 model actually is going to be pretty good at capturing the structure in the data. Of course, there's remaining energy, okay, but it's going to be interesting to take a look at what happens with this rank 2 model. So let's take a look at the right singular vector that ties the temperatures to this first factor. So it's always good when you're doing data analysis to try to imagine what you're going to see when you look at this. So right now we're going to look at a pattern of temperatures through the whole year, such that if I multiply it by a constant, so I scale it in different ways, I'm going to get the temperatures at all of the locations, okay, where each location is going to have a coefficient associated to that. So how do you think that pattern is going to look like, this pattern for the whole year? How is it going to look in the summer? How is it going to look in the winter? So what happens is, and this, we're looking at the United States, and that's important, right? Because otherwise we're looking at some other, like at the equator, this wouldn't be necessarily true. But in the winter, it's essentially cold everywhere. In the summer, it's warm everywhere, and that's the first factor. Okay, this seasonality of the temperature. And in fact, when people actually build models for weather prediction and so on, they usually hardwire this kind of seasonality because it's just there. So you might as well hardwire it. So what happens, do you think, if we zoom in? If we zoom in and you look at a few days, what do you think you're going to see? What happens in the night and what happens in the day in most places? Well, what happens if we zoom in is that it's cold in the night and it's warm in the day. So you get this periodic, again, like this seasonality if you want, but like daily. I don't know if that's called seasonality anymore, but like daily periodicity if you want. Okay, and here I'm showing you what happens in April, August, and December, like a week in each of these months. Okay, very interesting. So now remember that the way the low rank approximation works is that there's going to be a coefficient for each station, each weather station, that is going to be multiplying this right singular vector. So where do you think that this coefficient is going to be larger and when it's going to be smaller? And I'm going to give you maybe an example. Do you think it's going to be larger in New York or in Hawaii? So if you've ever been to Hawaii, in Hawaii, the yearly seasonality is not very marked. They're very lucky. It's warm all year long. In New York, if you've ever been in New York, seasonality is super marked. Unfortunately, like winter is super cold. And some people like seasons, so maybe those people say fortunately. I don't really. I mean, I don't like cold. But anyways, let me not start saying whatever. So yeah, let's take a look. Here, what I've done is I've drawn a marker for each of the weather stations at the corresponding latitude and longitude. This is why this looks like the United States map. And the radius is proportional to the corresponding coefficient. So we see that in Hawaii, indeed, the yearly seasonality has a very, very small coefficient. And in New York, some of these are, like one of these is New York, the coefficient is really large. In Florida also, seasonality is not that strong. And also on the coast of California, if you've ever been, there also the weather is actually, it's less nice, less warm than in Florida or in Hawaii, but it's still very constant throughout the year. Okay, so this makes a lot of sense. And the more you go to the interior, the more extreme this yearly seasonality is. So, this makes sense. Now let's take a look at the second factor, and in particular the second right singular vector associated to the factor. Here I didn't know what to expect. I'll give you, a few seconds if you want to try to think what could be this other term that actually makes a difference. So think a little bit about it if you want. In fact, I will show you this, because if you look at it like that, you can't really see much. Or at least I can't see much. And if you can, please let me know, because maybe there's something interesting here that I'm not seeing. So do let me know. If you zoom in though, you do see something kind of interesting. Okay, so here, just for clarification, I'm still showing you the first, this first term that captures seasonality. But superposed to that, I'm showing you this other term. And I have to tell you that it's quite noisy. Sometimes you see things like that. Clearly, it actually there's other fluctuations in here, but consistently you end up seeing things like this. So again, maybe I'll give you a couple of seconds to think what's going on. Realize that this guy, by the way, once you multiply it with a singular value, is going to be much smaller than this other guy. And I don't know, maybe I should have plotted it in that way. Maybe. So it's actually a correction, if you want, to this guy, once you multiply by the corresponding singular values. And this correction, what is it doing? You can see that it's kind of adding stuff here and subtracting stuff there. Adding stuff here, subtracting stuff there. Adding stuff here, subtracting stuff there. So it seems it's almost like a first order Taylor approximation, if you want. Right? Like, look, this is kind of like almost a diagonal like that. It's shifting this pattern to the left. Why would you want to shift that pattern to the left? Well, it turns out that the sun rises in the east earlier than in the west, right? So you might want to shift this pattern to the left for eastern locations and shift it to the right by multiplying by -1 in the western locations, to account for the fact that it's going to be warmer earlier in the day in New York than in California, where it's still night, or definitely in Hawaii. Okay. So what do you expect to see when we look at the coefficients corresponding to the weather stations that are associated to this factor? I kind of gave it away when I was describing the situation. We're going to probably see that on the east this is positive, and the west it's negative. And that's exactly what we see. Okay, so here the markers in white have a positive coefficient, the markers in black have a negative coefficient, and the radius of the coefficient is proportional to this term. Notice that it's not necessarily true that you go from very big to smaller to very big. You kind of do, but not quite. And the reason is that there's two things happening here. On the one hand, indeed, like you see how much correction you're applying, and that's why these guys are super small, because that's kind of the center if you want, and then it's correcting in one direction here and the other direction here. The other thing to take into account is that there's other factors. So some weather stations might not have as much weight on the yearly seasonality. So then this coefficient is also smaller. Okay, it's tied to the first coefficient in that sense. Maybe we should normalize by the first coefficient, and this pattern would be much clearer. Okay, and that's why these guys are smaller, even though they're very much to the west. Okay, probably if we normalized by the first coefficient, they would blow up as they should, because again, this accounts for this time difference. I didn't expect this when I analyzed this data, and I think it's pretty cool. Maybe it's the prettiest graph I've ever plotted. Okay, so what have we learned? We have learned how to fit and interpret low rank models using the SVD. Thank you very much.